Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will explore a ResNet, a most famous architecture in CNN or deep learning world, right? So far we had explored a fundamental architecture of LXNet and VGGNet, which play a crucial role in advancing a computer vision task, right? LXNet was introduced in 2012 and VGG was in 2014. LXNet was the first model which reduced the ImageNet error significantly, right? While VGGNet showed that the deeper model can capture a more complex pattern and we can improve the result, right? But as model become a deeper, it has another challenges, right? So as we try to build a deeper neural network or deeper CNN network for better accuracy, it has its own problems, right? So first of all, after some layer, it start increasing the error, or you can say overfitting. Or second problem is it can face a vanishing gradient problem, right? To solve this problem and build a deeper neural network, the ResNet was introduced, right? So let's understand what is the ResNet, right? So first of all, ResNet is a short form of residual network, and residual network has a residual block, or you can say a skip connection, which solve the problems when we create a deeper network, right? So we'll understand what is the skip connection. Okay. And one more thing, the ResNet win the first prize in the ImageNet in 2015, right? So the core idea behind the ResNet is a skip connection. So let's first understand what is the skip connection, or it's also called as a residual block as well, right? So if you see this diagram, and this whole part called as a residual block. So think it as a any layer, or you can say deep neural network dense layer, or you can consider it as a CNN layer. Okay, so as we are talking about the image, let's see, this one weight layer is basically one convolution block followed by a ReLU, right? So let's suppose there is one input going through this convolution block, right? And after the output of this convolution block pass to the next convolution block, as we are doing in VGNet and LXNet, right? One after one. But in residual or skip connection, what we are doing, the X will follow this path as well, but we are providing this X information directly to here. So we are skipping these two layers and we are directly adding or bypassing this X here, right? So now this point has this information as well, and the processed or transformed information as well, right? So this is a basic about a skip connection. Now how it will be helpful? Okay, so let's see. So let's suppose first case is identity mapping, right? So let's say while you are training a neural network, at some point your weights are becoming very small value, or let's say your f of x or output of this layer is very near to 0 or almost 0, you can say. Okay, so in that case, as you are passing this x directly here, okay, so if you are facing here a 0 output or any irrelevant output, right? So this x is directly passing here, and the next layer will have some value which is directly this x. So you are skipping this layer and you are passing directly to the x. So this x can be passed to the forward, and it will work as an identity mapping. So this two layer will produce some 0 output and you are still passing this. So next layer will understand or can process this input as well, right? Or at this point, if you are not getting the 0 or any kind of irrelevant output, let's say, so you can this next layer can understand this as well, and this transform the output as well, right? So it has a better information, I would say. Okay, so this is the one advantage, which is identity mapping. Okay, and second thing, as we discussed, like when you are creating a deeper neural network, you will face a vanishing gradient problem. Okay, so now how it will solve the vanishing gradient problem here, right? So let's suppose while back propagating, so first of all, vanishing gradient is a problem where your gradients are becoming very small or near to 0, hence your weights are not getting updated, right? So if you want, I will create a new video on vanishing gradient. Please write in the comment section if you want that, right? So let's suppose at this layer you are facing a vanishing gradient problem. So now where weights are getting very small due to the chain rule and passing here. So these weights are not getting updated, right? So but at this point we have two paths, right? This one which is straightforward and this second is a skip connection. So whatever layer here can get this gradient as well, right? So this layer will not face a vanishing gradient problem. So hence the next layer will also has a skip connection. So this layer will have very less chances to getting a vanishing gradient problem, right? So these two problems are solved there. Hence we can create a deeper neural network as much as we want. And this model was introduced in 2015, but this skip connection technique, right, is used in more almost many neural network, right? In transformer as well we are using this kind of connection which is called a skip connection. Not the same, but this idea is taken in multiple models as well, right? So if you see the paper, this is basically a paper which shows like when we use residual block we are having a less error with the same iteration, right? So if you see, this is the plane network. So plane network is nothing but the simple straightforward convolutional neural network. You can consider it as a VGG19 or something like that, right? So here they are using basically 18 layer and processing the training to 50 iteration. Okay, it's for both. One is ResNet with 18 layer, one is ResNet with 34, and plane network with 34 and 18. Okay, so if you see with the 18 layer, we reached at good accuracy, right? Which is in the plane we are reaching 27.94% and here 27.88. So here also error are reduced. But as we are increasing a depth, right? So if you see from 18 to 34 layer, plane network started increasing the error, right? From 18 we were having 27%, but at 34 we get 28%, right, error. And while with the ResNet with 34 layer, the error was reduced significantly, right? From 27.88 we reached at 25.03%, right? So this is one comparison that residual block or residual network perform better when we have deeper neural network, right? Okay, this is the one case. So this whole structure called the residual block, which contains the two layer, or in our case two convolutional layer, right? And we are skipping this connection here as well, and basically we are adding in here output. If you see f of x, if you consider these two convolution blocks output as a f of x and this x, so you are passing this x directly and adding here, so our output will be f of x plus x, right? So here as we are doing addition, right, so this x and the output of this f of x should be a same in the shape, so we can perform addition, right? So these two can be these two must be a same size output, right? So for that, if we are this let's say this convolution block is dividing the output or is producing a smaller size output, right? So we need to perform some operation on this x to make same shape, right? So for that we are using 1x1 convolution to reduce the let's say reduce the channel number of channel, or whether it can be a in size as well, right? So we are using 1x1 convolution there. Okay, and the second thing, this model also use the batch normalization. Okay, so let me explain in the brief what is the batch normalization. If you want, I can create a separate video on that as well. So already we know what is the normalization, right? So we are just making our data into the same scale basically, right? So let's say if you are doing standardization, so your data would be a mean center and one variance, right? Where will be mean will be 0 and variance would be 1. Same is if you are doing min max normalization, your data will be range in -1 to 1, right? So or 0 to 1. So same thing what we are happening here. So let's say you are creating a deep architecture, okay, and your input will be multiplied with many layers, right? So whatever in the neural network, ultimately we are doing matrix multiplication, right? So let's say your input here following some normal distribution, okay, hence we are converting into multiplication, addition, and that kind of operations are performed here. At some point, let's say here, your value can be drastically changed, right? And this, for this layer, at the first iteration it might follow some distribution, and second time it might follow some other distribution, right? So that will impact the training process, right? So optimizer will not get the better output, right? Or cannot train model in the better way. So what we are doing, at let's say after this one convolution block, whatever we are getting here output, we will scale that output, or you can say we are normalizing that output, or particular that batch, right? When we are training the neural network, we are performing batch wise, right? Forward propagation and backward propagation. So at particular batch in training process, we will normalize this particular batch, and then that batch will be passed on to the next layer, so that that particular layer can understand this in a proper way, and there is it's called as an in covariance shift basically. So we are solving that problem here using batch normalization, right? Okay, so now let's see this table. There they have mentioned everything about that. If you see, they had trained 152 layers, right? In VGG 60 we had seen there are 16 and 19 layers, and after that it was starting like producing more error, right? Error was increasing after increasing the layers. But in ResNet we can train till 152 layer as well. Okay, so first of all let's understand this table, right? So in ResNet, first layer would be a convolutional layer, simple convolutional layer with 7 cross 7 filter size. Number of filter would be 64 and stride is 2. By the way, this is the actual ResNet paper, right? So they had mentioned very well each of every detail, right? So this convolution operation will provide a reduced size, right? Because we are using stride 2 7 cross 7, and we are will not use any padding. Okay, so this output will be converted into a 56, right? After that we can apply a max pooling. Okay, it will also reduce the size, right? So till now this is only one convolutional block followed by the max pooling, simple. So now from here we having a residual block. So when they are writing 2, that means they have two blocks. So basically this is one block of residual block which will contain two convolutional. So when they are writing 3 cross 364, it's nothing but this one part which will contain a kernel size of 3 cross 3 and number of channel will be 64, and this kind of residual block will be a 2 here, right? Okay, so how this 18 layer would be there? So if you see this kind of blocks are 2, so you can see the 2 into 2. So there is basically this 4 into 2 8, and 9 into 2 16, and after that we have this one convolution which is 17, and last we have dense layer or fully connected layer which is 18, right? So hence it has the 18 layer. Same you can consider here as well. Okay, so this is the architecture, and they have mentioned like when we are if you see here the size is reduced, right, from 56 to 28. So this is reduced by a first block and first convolution rate. So you can see that convolution 3 underscore 1. So if you see here, so this layer will reduce the size, this will not change the size of the output, right? Because we are only converting one time, right? From 56 to 28, that's it. From 28 to 14, that's it. But after that next block, this block will not change the output shape, right? Okay, so let's get implemented so you can get the better idea on this, right? Okay, so first of all let's create this residual block so you can get a better idea. Then we will implement the ResNet whole neural network, right? So first of all let's build a residual block. So as we already used the torch view for the visualizing the model, and these are the three packages which we are using, basically torch, NN, and the torch view. Okay, so let's start. So first let's create a class which will be residual block. Let's say nn.module. Let's call super constructor which will be residual block self, and call the init. Okay, sorry, I need to create first init method, right? create the init self. Right, it will require the input channel, right? So basically a input shape and output shape. What is the output here? Okay, so I'll write the code, you can understand at that time. So let's say in channels, out channels, stride. Let's say by default stride is 1. Okay, it should be 1 tab. Okay, right. So first of all, let's create one convolutional block followed by a batch normalization and ReLU. As we know, this ResNet used batch normalization, right? So let's see self.con1 first convolution and then dot. So I am using the sequential model to get it better to understand. Okay. So first will be convolution 2D. C would be capital. So let's say con 2D in channels. Let's say in channels will be the in channels will be passed here. Let's say out channels will be out channels and stride would be whatever they will pass, right? Let's say stride will be stride and padding we are passing 1. So if you are passing the stride is equal to 1, it will not change your output shape, right? So let's apply batch normalization, batch norm 2D, right? And let's pass out channels will be as an input, right? Number of channels. And now we need to pass a ReLU as well. Let's say this is the issue nn dot ReLU, right? So this will be our first convolution. So you can consider it as an this weight layer, right? Now we will implement this second weight layer. Okay, so second of weight layer will be self con 2D. It will be capital 2D is equal to nn dot sequential say nn dot con 2D. So it will receive the out channels, right? Because we will pass the output of con 1 into con 2D, right? Let me write it as a con 2. Okay, so it will receive output channels and produce this output shape as an output channel as well, right? So as we know, the first part will change the output if required, the second will not change the output, right? Here they had mentioned like on 3.1, 3.4.1, 5.1 which tried to will perform the downsampling, right? So what same we are doing here. So it will receive the input channels and output channels. Stride will be 1 and padding will be 1 and kernel will be 3 cross 3, right? Let's say kernel size is 3. Okay, so here we are also missing the kernel size. Let's just provide that, right? Let's say kernel size is 3. So in all the residual block, according to the paper, they are using 3 cross 3 kernel size. Okay, so let's see, this is the out channels, right? So now this will followed by a batch normalization, right? Let's say batch norm 2D, this nn dot batch norm 2D which will pass out channels, right? Okay, so this will be our second convolutional layer. And then at the end, after, if you see this diagram, here we are applying ReLU, but after getting this output, first we need to add this output and then we will provide ReLU, right? So we will pass the ReLU in the forward method of this. We will just define here self.ReLU will be nn dot relu, right? And now let's sell self dot out channels will be out channels. Okay, simple. I'll explain why we are writing this when we will create the ResNet network. Okay, so now we had created this, but the one problem is, let's say we had seen this x and this f of x output should be in the same shape, right? Otherwise we cannot perform the addition. So if there is a downsampling, let's say input channel and output channels are not same, or we are performing any stride 2 or something, so we need to process this x to be same shape to the as per the f of x, right? So let's write that. So let's say first of all self dot, let's say downsample, first we will pass the none. Okay, then what we will do, let's say if stride not equal to 1. So if we know we are using padding 1 and kernel size 3 which is fixed, but if stride is equal to 2 or 3 or whatever we are providing, in our case we will provide only 2 or 1, right? So if we are providing stride 2, it will definitely reduce the size, right? Or output channels, right? So let's say not the output channel will be reduced by the stride, but at least it can reduce the size of the output, and output channel will be reduced by out channels, right? Or basically if you are coming from the TensorFlow, it can call it the number of kernel, right? Or let's say in channels not equal to out channels, right? So if in channels and output channels are not same, so we cannot add x and this output of this residual block, right? So we need to perform some operation. So what we will do, let's say self dot downsample will be, I am just creating one sequential block which will use 1x1 convolution. Okay, so let's say sequential, and first will be nn dot con2d, will pass in channels because input will be this, right, in channel, and then we are processing that, and will pass out channels will be out channels, right? And here will be kernel size will be 1 because we use 1x1, and we will provide same stride as we are providing here, right? So it will reduce the size if we require number of channels or let's say actual size, right? So if you see here, like for example, here we have 56 plus 56 output size with 64 channel, right? Then we are changing it to the 128 channel and 28 cross 28. So this might be we need to downsample or upsample this number of channels, or might be we require changing or downsampling the output size. So these two operations will be performed by this 1x1 convolution block, right? So I am just applying the stride here. Okay, and then it will also follow the batch normalization, the batch norm 2d. Okay, and we will pass the shape as an out channel. Okay, so this will perform as a downsample or upsample, whatever we required at that time. This downsample sequential model will do our task. Okay, now let's create the forward method. Let's say define forward. Okay, so first will be self, then it will require the x, which is the input. Okay, so now first of all, let's say residual will be our x. Okay, so for example, if there is no downsample, if no downsampling is required, we need to pass x directly, right? So let's first perform that. Let's say out is equal to self dot, first we will apply this convolution 1 which we had created to the x, and then second convolution block which we had defined, and it will receive the out. Okay, so now we reached here, we perform these two tasks. Now we need to check if there is a downsample required or not. So let's say if self dot downsample, if it has any model, otherwise it will be none, right? So if it has, then we need to do change the residual, right? The change, we need to change the shape of x. So residual will be self dot downsample sorry, downsample and pass this x, right? So now we change our residual as well if required, and then we need to add basically simple out, let's say plus or equal residual, right? So this part is done, this one f of x plus x. So you can consider this out as an f of x, and we are adding this x as well here. Okay, if required we need to downsample, otherwise as it is identity mapping, right? And last step we need to apply relu, right? Let's say self dot relu, sorry, yeah, self dot relu, we are passing the out, and this out will be returned. So this will be our residual block, which is we had defined here, right? Let's run this to check is there any error or something. No, I think it's we can move forward. Okay, so now second thing, we had created this residual block, now we need to create whole network, right? So if you see this part we had created which can provide a skip connection, now the whole network is remaining, right? So now let's create a whole network, right? So let's say class ResNet, we are using 18. Okay, let's say ResNet 18, same nn.module, define init, we are passing self block. So basically we are passing how many blocks we require, right? Let's implement it, then I will explain what we are doing. Okay, so block will be basically this residual block we will use, right? And how many layers we want that block we will apply, we will provide that information in the layers, right? So layers and number of classes, so we are providing 1000 as like that is introduced in ImageNet, and ImageNet has 1000 categories, right? So same, let's first create super ResNet self init. We had used ResNet 18, right? So let's pass that. Okay, now let's first of all let's create this part, which let me explain. So this one 7x7 convolution followed by the pooling, right? Here they had mentioned here. So we had particularly clear a residual block created, and now they are applying this first layer first of all. So it will be, let's say self dot convolutional 1 will be, I'm using sequential here, let's say nn.con2d. So input channel will be 3, right? Let me write input channel will be 3 because we have 3 channel inputs, right? As you know, 224 cross 224 cross 3 is RGB. Okay, and number of in planes will be, we required 64, right? So if you see here, basically we are providing a 64 kernel of 7 cross 7, right? And let's me write here out channel 64, kernel size will be 7 cross 7, stride is equal to 2, and let's say padding will be 3, because if you see this table, from 2 to 4 we need to convert into 112 size, right? Output size. So they had not mentioned the padding properly, how many padding is required, but if you calculate this in LXNet, we had implemented a function which can calculate the output shape, right? So you can check that video as well. So if you provide a padding is equal to 3, you will get this 112 output size. Okay, so this will be padding is equal to 3, and it will followed by the batch normalization, batch norm 2d, out channels. Okay, so out channel will be here 64, right? This one, and then at the last we will provide relu, right? So let's say nn dot relu, done. So this first part is created. Now second would be our max pooling, right? This one 3 cross 3 kernel size, max pool, stride will be 2. So let's say self dot max pool will be nn dot max pool 2d. We will pass kernel size will be 3 cross 3, stride will be 2, and padding will be 1. So this will also reduce our output size, right? So this two part is created. Now the part is we need to create this part, basically a residual block, right? Okay, so let's say first of all we are creating self dot layer 0. So layer 0 basically means the first residual layer, right? So let's say, so first of all let's build a function which can call this part, right, this residual block. So let me create one method. Let's say define. I am using this underscore here, so it can, you can consider it as like a protected or private method, right? Let's say make layer first slab, first will be self, then we'll pass which block we need to use, and let's say it would be what we would require, output shape, right? Output channels. Second thing we will require block, how many blocks we need to create. So this block will be our residual block, and these blocks will be a list, or you can say number, how many blocks we require. Here we are using 222, right, for the 18 layer. Okay, so this will be the blocks, or let me write it number of blocks, right, it would be better. And second thing will be which stride we need to use, it will be default as a 1. Okay, so now first of all let's say layers would be the list, because we need to create multiple layers, right? For first part we need two layers, then we need second we require again 2 layers, right? So let's say layers and layers dot append block self dot in planes, right? So if you see in planes is basically where we reached, right? So let me write here, let's say self dot in planes. So first of all we are creating 64 planes, or let's say I'm just writing self dot out channels, right? It would be better to understand. So first of all we required 64 as an output channel, right? So first of all we are adding this block, let's say self dot out channels. Okay, so first residual block will receive a 64 as an in channel, right? Correct. And now let's say second will be out channels, which we are passing here. Okay, so second will require the out channels, and third will be stride. So stride we will pass from here. I'll explain. Let me write it first. So first what we had done, we had created this block with this first. So if you see, if you are creating a 2 blocks at a time, only this one at the first time, first convolution block will reduce the size. So whatever stride will change at the first time, right? So that layer we are appending separately. So now let's say I can write the for loop, let's say for I in layers, or number of blocks we can say. So let's I in the number of blocks. So first we had created this first layer as well, right? So let's say it would be range, because first block will be created as the stride whatever we will pass. From the second onwards, next block will contain stride is equal to 1, right? So number of blocks we will start from the 1. So it will iterate less than 1. If you are passing number of blocks 2, then first block will be created here and second block will be created in the for loop, right? Because we are starting from the 1, so if you are passing 2, it will iterate only one time, right? So let's say layers dot append, we are appending the second block of the residual, basically residual block, right? So it will be also block self dot in planes and it would be in plane should be, we had mentioned, right, in channels basically, not the out channels, it would be the in channels, right? So let's say self dot in channels, and then we require the output channels, and then stride will be default 1. So we are not passing, it's okay, because the block contains basically stride 1 by default, right? So here we are only passing out channels. Out channels will be this, spelling mistake is there, it should be double end, right? Let it be this, like this. Okay, so now this is about make layer method, okay, and it will return. So we are just appending a layers which we will create, and I am just passing here return nn.sequential. So all layer will be combined and will create one sequential block, or you can say one sequential model, right? So let's say layers. Okay, what happened to it? Self.out channels. Okay, it should be in channels, and we need to use double N. Okay, so this is the created. Okay, so first of all, let's see what we are doing. So let's suppose here they are mentioning 2 blocks, okay, of residual block, 2 residual block basically. So let's create self dot layer 0 will be self dot underscore make layers, which we had defined here, right? And this one, in which we will pass, first of all it required block, okay. So block is nothing but residual block. In the out channels how many we require? We required 64, right? If you see here, we required 64, right? It would be a 64, and layers would be layers of 0. So we are passing here layers list, which in our case when we are creating ResNet 18, it will be 2, 2, 2, 2, right? So let's say here layer of 0 contains 2 blocks, right? Basically we require to build 2 residual blocks. So and stride will be 1. So here we are not changing the shape, okay. Let me see. Okay, from 56 to 28, so I think it will reduce the size, okay. So we need to pass, first of all, let's say stride is equal to 2, right? And then we pass same layer 1 will have 128, right? So let's say 128 channels, layers of 1, stride 2. Okay. So if you see, they mention the downsample is performed by convolution 3, 4 and 5. So first this one will not reduce the or not do the downsampling, right? So here stride will be a 1, and from 128 we are providing 256 number of channels, and then 5 and 2, okay. So we are passing the same, it would be 5 and 2. So basically we had created a 4 residual block. Each residual block contains a 2 convolutional layer, right? And we had created for each layer 0 will contain 2 residual block. Each residual block contains 2 convolutional layer, right? Simple. So now we had created this layer. Now let's create fully connected layer, right? So we reached till here. So now if you see at the end, after converting 5 and 2 number of channels, right, we will use average pooling, and then we need fully connected layer, right? So first of all, let's see fully connected. So it will be nn.linear, right? Let's say they haven't mentioned like how many size of fully connected layers they required, but let's suppose we are passing here 5 and 2, right, and converting into. So okay, so they are using directly the last layer as a considering as a fully connected, which is the number of category, and then what we are doing after getting this output, when we apply the max pool, right, average max pooling, we will receive 5 and 2 cross 1 cross 1, if they had mentioned here, let me see. So after when you are creating this, output shape will be 1 cross 1, right? And we have 5 and 2 channels, so it will be 1 cross 1 cross 5 and 2. Hence we are creating a linear layer which input will be 5 and 2, right? So now let's create a forward method of it. Okay, define forward, let's say self, and it will receive the x. Okay, so now first of all, let's say x will be, so first we need to call this convolution first block, right? Self dot con1, and it will take x. Now we need to provide the max pooling, self dot max pool, we will pass the x. Now we need to apply our residual block, or you can say layers, right? So let's say x is equal to self dot layer 0 of x. Same thing, we will pass, let's say layer 0, layer 1, layer 2 and layer 3, right? After this we need to perform average pooling, right? So let's say x is equal to self dot, so we haven't defined average pooling yet, right? So let's define that here. Let's say self dot average pool will be self dot self, not self, it will be nn dot, if you see average pool 2d, right? And what it will require, number of kernel size would be 7, right? And stride is 1. Okay, so this will perform the average pooling. Let's do now, we had defined average pool, x is equal to average pool, we need to pass x. And now after average pooling, as we know, we will get the output of 1 cross 1 cross 5 and 2. We need to flatten this area, right? So let's flatten this. We will use view, x dot view, x dot size of 0. 0 will be a batch size and rest of will be flattened, right? At the end we can apply self dot fully connected, which is our fc, and the x, and we will return this x, right? So this will be our ResNet basically. So now when we need to call this ResNet, okay, we need to define, first of all, let's say model will be ResNet 18, right? What we had defined, n is capital, right? Yeah, so ResNet 18, and first argument would be a block, right? N layers. So first of all, block, we require residual block, so it is residual block, right? And second, we pass layers, right? So first we need 2 residual block, then 2, then 2, and then 2, right? Simple as like this, 2 residual block, 2 residual block, right? And let's run this. Torch.nn has no attribute, sequential. Okay, spelling mistake is there, I haven't passed n, in which ResNet. Okay, so it will be sequential, right? Let's run. If there is any other typo, let's see. Yes, again here S should be capital. Let's see, is there any other? No. Okay, so this is about a ResNet 18, right? Similarly, you can create a ResNet 52, ResNet 34, or ResNet 152 by your own, so you can get better idea. Okay, so now let's visualize this model. So I am using the draw graph from the torch view, right? We will pass model, our input size will be 1, 3, 24 to 24, right? And let's say expand nested will be true, and we will try visualize the graph, right? Okay, now let's run this. Failed to run torch graph, see the error. Okay, given graph, weight 128, 63, expected 128, 28, 64, but got 128 channel instead. Okay, so here we need to update our in channels, right? Because after each layer, whatever the out channels, will be the in channel for the next layer, right? So let's say it would be out channel. Suppose, for example, here if we are downsampling or converting out channels, for example here from 128 to we are going 256, right? So that next time for this layer the input channel will be 256, right? So we need to apply here as well. So this in channel can be updated, and next time this out channels of the previous layer will be become in channel, right? So let's run this. Let's visualize if it is happening or not. Same failed to run. What is the issue? Let's see. The group 1 weight 128, 64 3,3, expected 128, so 64 channel but got 128 instead. Okay, we had done some mistake somewhere. Let's see, 64 128. This is the out channel. When we are passing the out channels, okay, this should be here, right? Because after first layer the out channel will be changed, right? So the next layer, for next layer in channel would be there. So I was explaining the same, but we should write it here because this layer will change the output, right? So let's run. Yeah, now we got the result. So we can visualize the model. So first of all, we have that convolutional layer with 7 cross 7 kernel size, right? We reduce the size from 112, right? From 2242. So if you see here, we have performed the sequence skip connection, right? From here, the output of this we are passing directly to here with the adding, right? Or doing the sum of that two, the output of this and particular the x. So you can visualize the skip connection here as well, right? So this is all about the ResNet. At the end, if you see, we have 512 1 comma 1, right? And then we had flattened that 1 comma 512, and then at the end we have 1000 categories, right? We can apply the softmax here as well, or you can apply the softmax in the training process, right? Yeah, so this is all about the ResNet. If you have any doubt, you can ask in the comment section, we can discuss there. And if you like my video, please press the like button and subscribe my channel for more content. Thank you.